first two papers will be 20-minute presentations followed by a 5-minute Q&A session. And the short papers will be 5-minute presentations without Q&A, but you're welcome to follow up with the authors after the presentation. So the first talk is from University of Toronto. It will be on debug, efficient debugging in FPGAs. It will be presented by Sameh Attia. Sameh is a PhD candidate at the University of Toronto. He received his Bachelor of Science and Master of Science degrees from Cairo University, Egypt. His current research interests include FPGA debugging, CAD, and hardware checkpointing. Please welcome the speaker.
Thanks, Attia. Good morning, everyone. So, in this talk, we present StateMover, which is a new debugging tool for FPGAs, which combines hardware execution and simulation. So first, why we need new debugging tools? I think the main thing is that FPGA designs are getting more complex, which not only increases the CAD runtime, but also the time to debug these designs. A study in 2018 shows that 50% of the time, project time is spent in verification. And as you can see from this curve, this percentage is actually going up. And almost half of this time is spent only in debugging. So we need more efficient debugging tools. Maybe the second motivation is that FPGA are being deployed in data centers. So you have multiple FPGAs and CPUs collaborating together. So if a crash happens or something goes wrong, you have to have a full visibility of what is going on inside these FPGAs so you can debug the cause of the fault. So what we have right now? Right now, if you want to debug an FPGA design, you have two options. First one is to do a simulation where you have full visibility of all the signals, but it's very slow. So it can take you 5 years to simulate Linux booting on a multi-core processor. You have another option to run your design on FPGA, so you can run it at full speed, but you will end up moving from the full visibility of signals to a black box. There's some on-chip debugging techniques that tries to add more visibility to your design. One of them is trace-based techniques, which are using embedded logic analyzer to like chip scope and signal tag to add more visibility. So basically, it allows you to run the design at full speed, and you will have to select some signals to record their values at a certain trigger condition. So to record these values, you will need spare on-chip resources like VRAM, and if you cannot debug the design for the selected signals, you have to reselect the signal or change the trigger condition. So you have to go into a design recompilation, which takes hours. There's also, you can do also incremental insertion. It also takes some time, way less than design compilation, but still some time, and it cannot be very easily done on highly utilized FPGAs. You can also use readback. So readback is use the existing configuration architecture to read back the register, lookup tables, and RAM contents out of the FPGA and dump it into readback file. So it doesn't require any additional access hardware and give you full visibility of register and lookup tables and program. And it is available on Xilinx FPGAs and recent Intel FPGAs. But still, readback has some weakness. One of them is for sure, it is difficult to use since we have to post-process this readback file. You have 4 zeros and 1, and you have to post-process to know which is the value of your register you want. Another drawback is that, or the major one, is that you have to stop the clock. So think, for example, if you have a design with multiple clocks, you have to do it safely to get a consistent state. If you have a design interfacing with an external DDR and you stop your design in the middle of transaction, you can get data loss. So you have to handle that carefully to get a consistent state and to allow the design to continue execution later. Another drawback of readback is that it doesn't provide you with signal history, which means that every time you read back, you will get only one value for each signal. So it doesn't allow you to see how signals evolve over time or change over time. So as you can see, there is no existing solutions that give us everything we need. So can we have a software like debugging, which means that full visibility at a reasonable runtime? We believe that to achieve full visibility, we have to use feedback. But can we overcome the weakness of feedback? Difficult to use, inconsistent data if you have a complex design with multiple clock domains or multi-cycle interfaces. Overcome the problem of no signal history. That's why we present StateMover. So StateMover is a debugging framework that's based on hardware checkpointing. Hardware checkpointing is taking a snapshot of the design state that can be used to resume the execution later. So StateMover basically allows you to move the design state back and forth between an FPGA and the simulator, which we believe enables new debugging flows for FPGAs. So first, it safely interrupts your design, whether it is running on an FPGA or a simulator. If you have a design running on an FPGA, it allows you to read the on-chip state of the design, move it into a simulator where you can see all the signals and have full visibility of what was on the FPGA. You can actually continue the execution on the simulator, so you will see how signals change over time and help you debug your problem with the full capabilities of a simulator. And after you run it on the simulator, you can also extract the design state from the simulator, move it back to the FPGA, and continue the execution starting from this point. Since you can change any signal value inside the simulator, this gives you full controllability on your FPGA design that's running on the FPGA. So basically, it gives you the best of two worlds. It combines the speed of hardware execution and the full visibility and controllability of a simulator. The tool flow is simple, so basically we will provide you with some interruption logic that tries to safely interrupt your design. You will run through the normal implementation flow, and then you run an extra script that dumps some information that we use. And when you want to debug your design, you will start two things: your normal simulator and the StateMover console. We provide you with some commands that help you move the design state back and forth between an FPGA and the simulator. So how does the StateMover work? So the overall infrastructure consists of your design on an FPGA connected with the interruption logic that we add, and the user interface, which consists of the simulator. We are using Model Sim, but you can use any simulator, and the StateMover console. And then the back end, which contains all the functionality, state extraction, and insertion. So let's go into details. The interruption logic, the main goal of it is to safely interrupt your design. So it contains of two blocks. The first block is breakpoint logic, which defines when you want to stop the design. It could be at a certain cycle, could be at a signal condition. And then the breakpoint logic requests an interrupt from the TI controller, task interruption controller, which try to safely stop your design. So if you have if you have a simple design with no multiple clocks, no multi-cycle in-out interfaces, we just stop the clock. But if you have a complex design, we first handle related clock domains and unrelated clock domains. We wait until in-flight transaction to finish while stopping the initiation of new transaction. I'm not going into details of that. It is published in our work, Feel Free to Interrupt, that's published in 3REDS 2020. But the main goal of the interruption logic is to safely interrupt your design. And then you have the user interface. As I mentioned, it consists of your simulator and the StateMover console. The StateMover console interfaces with the interruption logic through JTAG, so you can set a breakpoint, a hardware breakpoint where you want to stop your design. And then you have some commands to allow you to move the state back and forth between the FPGA and the simulator. So if you want to move the state from the FPGA to the model sim, for example, you will read back you will run the command read back. It will take the hardware state out of the FPGA, dump it in the hardware state file, and then you can load it into your simulator. You can also dump the simulation state in the simulation state file, and then write it back to the FPGA. The interesting thing is the hardware state file and simulation state file is actually checkpoint files, so that you can use it to resume the execution later, whether on an FPGA or a simulator. It's also readable, so it contains the signal name and the signal value. So you can actually use it to compare the on-chip simulation state, on-chip state with the simulation state at a certain breakpoint. And then comes the back end where all the functionality is done. The first part is CSR which stands for Context Save and Restore. The main goal of Context Save and Restore simulator is to extract and insert the state into and from the simulator. It is a C++ program that interfaces with your HADL simulator and can read and modify the simulation state. It has to do an extra step, which is matching each state element in the simulation model with the corresponding hardware element. So we are using a post-implementation netlist so that all CAD documentation are taken into account, but still we have to identify which state element in your simulation will be mapped to physical state elements. We have to do also some name matching between the simulation and the hardware files. Second part of the back-end is the state config, which deals with state extraction and insertion from the FPGA. So the first part, when you do a read, you run the command read back. We actually do a read back, and which is dumped in the read back file, and then we post-process this file to extract the state out of it. This is easy for registers that has only one bit, but if you have a memory, we have to do an extra step, which is physical to logical RAM mapping. Basically, we try to reconstruct the logical representation of a memory. So here's an example, for example. If you have a design with a 16-bit shift register, so you have a primitive SRI in your design, but what we actually read back from the FPGA is the content of the 6 input lookup table. So we have to map the 64 bits of the 6 input lookup table to the 16 bit of your shift register. Another example, if you have a memories that expand, distributed memories that expand multiple lookup tables, so we have to combine multiple lookup tables and map it back to your distributed memory in your simulation. Second part of state config is how to insert the state back into the hardware. So first we need to do the opposite of the physical to logical mapping, and we have to do bit stream manipulation. So basically we take the simulation state, embed it into a bit stream file, and then use the bit stream file to reconfigure the FPGA. We do support partial bit stream, which is very important if your design has reconfigurable partition, if your FPGA is a multi-tenant FPGA. So when, for example, we can support that you only stop one task that you want to debug, read back its state, write back its state without affecting other parts of the system. There's not much of public information on how to embed state into partial bit stream, so we have to do some reverse engineering, but yeah, it was fun, and we try to make everything in reverse engineering automated using scripts, so we can support future FPGAs. So here's the overall infrastructure of StateMover. Let's see some examples and the results. So here's an example session of StateMover. Basically, we have a design with a simple counter that increments every second. It runs on a 125 megahertz clock. When you simulate the design on model sim, it will take you 4 minutes to increment one time. So we let it run for 3 times, we let it increment 3 times, and that take us 12 minutes. Then because it is slow, we wanna make it faster, so we dump the state into the simulation state file and write it back to the FPGA. The counter is connected to the LEDs of the FPGA, so we saw 3 on the FPGA LEDs. And then we let it run for 1 minute until it reaches 62. We read back the hardware state and load it into simulator. This is an actual waveform of the model sim, so you can actually see 62 on the model sim. And it can continue running starting from this point, 63 and 64 and so on. So basically, this shows one of the most interesting features of StateMover, that you can use it to fast forward uninteresting periods of simulation. So if you have, for example, some periods that you don't want full visibility, you can let it run on the FPGA at full speed, move it back to the FPGA, to the simulator when visibility is needed. We tested StateMover on a lot of designs. We used built-in self-test design, so we wrapped our designs with a built-in self-test. Let it run first to generate a golden signature, and then we run it on an FPGA, stop it, move it into a simulator, continue the execution on the simulator, and generate another signature, compare the signature with the golden signature. We did that for a lot of design. One of them is logic, one of them uses DSP blocks, and one of them uses memory. We also tested StateMover on a big system where we only stop one task of the system that has an axis interfacing with the external memory, which is the AES design. We also did that for a big design to show the scalability of StateMover. All the testing is done on a Kintex AltaScale. So right now we support the AltaScale family, but as I mentioned, all our work is automated, so we can support any FPGA that has feedback. So what is the cost of the interruption logic that we add to your design? It has a very small area overhead, so it can be around 0.5% of the basic design. It has no timing overhead since it is added outside your design, just control the clock going into your design. In terms of checkpoint file size, for the biggest design, checkpoint file size is only 4 megabytes, which is small compared to the size of the readback file, which is 132 megabytes. In terms of the speed, how fast you can move the state from the simulator to an FPGA or from an FPGA to a simulator. So for readback time, which is moving the state from the FPGA to the simulator, for the biggest design, it took us 13 seconds to move the state. 10 of them is actually the readback utility itself of the FPGA, and then we post-process this information in 3 seconds. For the other way around, to write back the state into an FPGA, for the biggest design, it took us around 15 seconds. 9 of them is for writing back the state or reconfiguring the beta stream. And actually, the readback time, which is 10 seconds and 9 seconds, this is done for the entire FPGA. So this is the maximum number of seconds that will take us. This is fast enough when compared to the simulation speed as we're going to show in the next slide, but there is much room for improvement. So basically, the read back and write back is done through JTAG, which is slow. If you use PCIe, for example, it will be faster. The post-processing or the extraction and insertion of state is done in Python. So if you want to speed that up, you can do it in C++, for example. So we also compare the hardware to the simulation speed. So to measure simulation speed, we run a full functional simulation for a number of cycles for each design. The simulation is done on a full version of Model Sim on an Intel Xeon processor. You can see for the biggest design, the simulation is actually 11 million x slower than the FPGA. So this shows the productivity gains of using StateMover to run your design on an FPGA and only move it to simulator when full visibility is needed. In terms of feature work, readback doesn't support to read the internal DSP register or the input register of a block RAM. So we wanna support this register by, we have some ideas of how to do that, like multi-cycle capture and restore, adding shutter register, and we're working on that right now. We're also thinking, right now we only extract the internal state of your design, but if your design is interfacing, for example, with a DDR, you want to also capture these things. But you cannot actually capture or move the state of Ethernet. So we are trying to hook the FPGA peripheral to a simulator so that we can support Ethernet, DDR, PCIe. So in summary, StateMover is a new debugging tool that is based on hardware checkpointing. It allows you to move the design state back and forth between an FPGA and the simulator. It gives you the best of two worlds, combines the hardware, the speed of hardware execution with the full visibility and controllability of a simulator. It can also be used to fast forward uninteresting variable of simulation. Thank you.
Thanks for your talk. I wondered if you thought that StateMover could form the basis of an exhaustive simulator that kind of works by first running in hardware for as long as you can, and then when it comes to some sort of branch, some sort of decision point, it saves the state to copies it back, and then takes one of those paths, and then later on it comes back to the saved state and explores the other path. So this sort of together sounds like it could make an exhaustive simulator that would tell you all of the possible things that could happen.
That's interesting, yeah. So basically, you can checkpoint, you can move the state at any time from the FPGA to the simulator, and currently we are using a normal simulator, but yeah, it's a good idea of having multiple simulation on a given part.
Thank you, Master Group. Very interesting work. I have a question about can this framework deal with interact with the outside world like the Ethernet, DDR, or PCIe?
Yeah, so in our future work, we want to support that by basically trying to hook the FPGA peripheral to the simulator, so you still be in the system when you move from the FPGA to the simulator.
So the outside world is simulated in the simulator side, or it's actually connected to?
So right now, yeah, we use the simulation model for the DDR and Ethernet in the simulation, but in our future work, we want to hook the simulator to the actual Ethernet peripheral and DDR peripheral of the FPGA.
Thank you.
Oh, sorry, I was talking Patrick. When I'm debugging hardware, the most important thing for me is a trace. And I would like to see a trace, say, over 1,000 or 1,000,000, whatever number of clocks I use. Because I want to look at multiple waveforms concurrently, say, in the waveform viewer or something like that. That's the most common thing for people to do. So this is kind of a clarifying question. Does your tool accelerate that?
So basically, it doesn't accelerate the trace thing. So basically, if you want to see how signals change over time, you will have to move it in the simulator and run the simulator at that time.
Okay, so my understanding then is if I want to create a signal trace over time, then I am stuck with the slowdown in the simulator.
That's true. You can also combine the StateMover with normal trace space. So basically, use trace space for important signals that you want to see always, but only move the simulator when a full visibility is needed for a full debug.
But those would be two separate processes. I wouldn't be using the simulator when I'm looking at the trace. I have a separate tool for that.
Yep.
Okay, thank you.
I have two questions. First one is kind of a clarification question. In your readback diagram, do you still expect clock stopping during interrupt, or you expect the system stable after the interrupt?
Sorry, I don't get your question.
So do you still expect to stop the system clock to carry out read back, write back?
So we do stop the clock, yeah, but we do it in a safe way to. If you have a multiple clock in your design, if you just stop it naively, you will not get a consistent state. So we make sure that we do stop the clocks in a safe way.
Because interrupt is helpful to set up a clock stopping event.
How we use that?
Yeah, the interrupt, whatever. Task.
So basically, when we stop the clock, we are using a PUFG primitives. So just gauge the clock that is going into your task or your design. But we do it in a way that's safe. I think there's no details in our previous paper, which is free to interrupt here, on how we do exactly the safe thing to stop the multiple clock.
Second quick question. What's the method you use to correlate the register in RTL versus the technology map or synthesized register?
Yeah, so we are using both implementation method, which contains the parameter of the family you are using. So we know for each family which state element in the simulation model will be mapped to physical state elements.
Thank you.
Okay, let's stop here. Time, and please pull out the debug.
It's a very quick one.
No,
You have this-
no, no,